For the first question, we're asked to draw the mechanism and major products for the following reactions. We have epoxides for all of the compounds, all the first four compounds in problem number 1. It looks like for the first two, we're under acidic conditions for both. So as a quick reminder, if you're under acidic conditions, that means we're going to add to the more substituted side. If we're under neutral or basic conditions, we add to the less substituted side. So the more substituted side of our epoxides are this carbon here and this carbon here. And that's what we're going to use our nucleophile. In this case, we have weak nucleophiles for both. Our methanol or our Br- are the nucleophiles we're going to add to the less substituted side. All right, in the first step, always if we're under acidic conditions, we're going to protonate the epoxide first. So I'm going to redraw my HO H2 or my H3O+. We're going to protonate our epoxide with our electrons there to get us to our intermediate, which is the 6-membered ring. And we still have our oxygen on a wedge. Now it's protonated, so we have a plus charge on that. All right, and then we have water as a byproduct. Now, if you had water come in as your nucleophile, there's nothing wrong with that necessarily. If you have H3O+, comma, with another solvent like methanol, that's probably the more prominent solvent in solutions. That's probably going to be a weak nucleophile that comes in. Again, I'd give full credit for both because you weren't told exactly how much of each reagent that you have. But based on what I see here, it makes more sense to draw methanol as the nucleophile. So again, if we are under acidic conditions, we are going to attack the more substituted carbon of the epoxide. So when we attack the more substituted carbon, that means we're going to do a backside attack. So we're going to come from the back, essentially almost where this methyl group right here is, which means that methyl group needs to be pushed up. The electrons in this bond is going to break. Those electrons are moved to the oxygen to make an alcohol functional group. So looking at our next intermediate, we have our cyclohexane. We no longer have an epoxide. We do now have an alcohol functional group, which is OH on a wedge. So this bond here broke. This bond here is still there, and that is the bond that I drew there. So we have an alcohol functional group. Now my methanol came in from the back side, so that now needs to be on a dash, and it pushed all the other carbon bonds up a little bit. We're going to exaggerate that and say our methyl is what was pushed up mostly. So I got a little distracted there. I didn't finish drawing my methanol. Now we have a plus charge on our oxygen, we have a hydrogen there, and we have our CH3 there. And this methyl group right here, again, this methyl group that was on a dash is now pushed up to be on a wedge. So that is my CH3 or my methyl group. For the weak base that we're going to use, that's going to be water. Again, you could show methanol. Either way would be fine. Water or methanol would be our weak base to deprotonate the very acidic proton there. That gets us to our final product, which is our 6-membered ring, and we have our OH. Notice that for all addition reactions, if we have an epoxide, that's going to be converted to an OH functional group or an alcohol functional group. Now we have our methyl group on a wedge, so CH3 on a wedge, and our methoxy group or O-methyl group on a dash. For the next one, this is a little bit easier because we already have our acid drawn out, so we can show the proton transfer reaction. That gets us to our intermediate. Which is our protonated epoxide. Hydrogen and a plus charge, and we have our methyl group on a dash, and our Br- is our nucleophile. That's going to attack the more substituted side since we've protonated our epoxide. So that's going to break that bond right there. Again, our alcohol functional group will be on a wedge. Br came in from the backside. That's going to push that methyl group up, and our Br is going to be on a dash. So this is also convenient because we've actually formed our final product. In this case, there is no intermediate that needs to be deprotonated. Our Br minus is already a strong nucleophile. So for this, we have our 6-membered ring, and we have our OH on a wedge, and our methyl group is on a wedge, and our Br is on a dash. All right, for the next two, now we have a strong nucleophile. So for the strong nucleophile, we prefer less steric hindrance for a backside attack, so we're going to attack the less substituted carbon. So in this case, we already have Br minus, so Na plus Br minus. This would be the same thing as just essentially drawing Br minus. If you add this as a reagent, you're always going to add sodium or some salt associated with it to make the full salt, but this is Br minus doing the backside attack. So here we're going to have our electrons come in from the backside of our epoxide. So imagine Br coming in as and forming a bond that is now a dash, and these electrons go up here. And that forms an intermediate where we now have our 6-membered ring still. We've got our bromine, which had a negative charge. Now it's neutral. We use its electrons to form this bond. And now we have our oxygen, which is still on a wedge. And we have a negative charge in the oxygen because it gained electrons. And we have our methyl group. We do need to do a workup on this. We need to add a weak acid so that we can protonate that to form an alcohol functional group. So for the weak acid, if you wanted to say something like HA as like a workup reagent, or HB sometimes I use, so the proton connected to a base, or even something like H3O plus, all those would be fine. But you do need to show something basically giving this its proton. So I'm going to show that. Reacting with that, I'll go ahead and erase my HA, and that'll get to the final product, which is again a 6-membered ring, and Br, our alcohol functional group, is now on a wedge, and our methyl group is still on a dash. Alright, here we have sulfur with a negative charge with an ethyl group attached. Again, this is a strong nucleophile. It's going to attack the less substituted side. So for this carbon, looking at this carbon, we have a methyl group. That carbon's part of the epoxide. That carbon's part of the epoxide. So looking at things in excess of the epoxide, here we have one methyl group. Here we have two methyl groups. So this carbon is the less substituted side. It's going to do the backside attack. Again, this methyl is planar. That part of the epoxide is planar. That's on a wedge, so that means our sulfur is coming in from the back, so we need to represent that with a dash. So there is our sulfur, and that sulfur has an ethyl group attached to it. I didn't show this bond breaking, so these electrons move up to the oxygen, and now our oxygen is on a wedge that has a negative charge. And we have our methyl group there. Again, we need to do a workup with HB to get us to our final product, which is our alcohol. So sulfur still has the ethyl group, our OH is now protonated, and we have a methyl group attached right there. Alright, for the next one, provide common names and IUPAC names for the following ethers. The common name has ether in it. The IUPAC name calls those group ethoxy, or essentially oxy group. So in this case, this is an ethoxy group. In this case, this is also an ethoxy group. We'll look at that more in a second. So for the common names first, we're going to call it an ether, which means we need to specify what both of these groups are. So this right here is an ethyl group, and this right here is an isobutyl group. So in looking at the name, start out by basically, for the common name, start out by saying all of them are ethers. So that's a good starting point. That's, if you say the common name of an ether, it always ends in ether. All right, so for our substituents here, we have ethoxy. Sorry, not ethoxy. We have an ethyl group here, and we have an isobutyl group here. So looking alphabetically, ethyl comes before isobutyl. The iso group, whenever you see iso, that counts as alphabetically, but if you see tert or sec dash to whatever the group is, usually a butyl group, those do not count alphabetically. So in those cases, if you start with the butyl group, you'd start with the B. So usually those are going to be early in your name rather than later. In this case, ethyl comes before isobutyl though. Ethyl wins, so this is ethyl isobutyl ether. Ethyl isobutyl ether. Let's do the next common name here. We'll go back and do both IUPAC names. So in this case, we have 1, 2, 3, 4, 5 carbons. So that's pentyl. In this case, we have sec-butyl ether. So our methyl group is coming off that first carbon. We have 4 total carbons in this, so this is referred to as sec-butyl. Again, in terms of arrangement, it's alphabetical, but we don't look at the T or the S of set or tert, of sec-butyl or tert-butyl, so those are ignored. Butyl comes first, so this is sec-butyl. And then pentyl ether. All right, now for the IUPAC names for these two, we're going to call them ethoxy groups. So essentially, the smallest ethoxy group is the group, and the reason why is because we need a parent chain. So in this case, our parent chain, the longest carbon chain we have is 1, 2, 3 carbons, so this is propane. We have a methyl at carbon number 2, and our ethoxy group is at carbon number 1. So here we have carbon number 1, 2, 3. We have our ethoxy group at carbon number 1 and our methyl group at carbon number 2. So this is 1 ethoxy, 2 methyl propane. And then for the next one here, this is pentane. So we have 1, 2, 3, 4, 5 carbons. That's our longest carbon chain. And then at carbon number 1, we have this group here. So for that group, that is our sec-butoxy. So instead of sec-butyl, we're going to say sec-butoxy. And again, that's at carbon number 1 of our 5 carbon chain, the longest chain, our pentane chain. So we have 1 sec-butoxy. Again, just like our, instead of ethyl, instead of our sec-butyl, now it's butoxy. Instead of ethyl, it's ethoxy as our substituent on our parent chain, which is pentane. All right, for this compound here, again, we have an ethyl group and we have a tert-butyl group. Butyl comes before ethyl, so this is tert-butyl. And then ethyl ether. We'll do the common name again for this. So here we have our propyl group, 1, 2, 3 carbons, propyl, and then we have an isopropyl group. Isopropyl starts with I, that comes before. And again, the easy way to remember is the isopropyl doesn't have a dash. If it has a dash, you don't count the first letter. If it doesn't have a dash, you do. Isopropyl doesn't have a dash in front, or the iso doesn't have a dash in front. So this is isopropyl, and then propyl ether. All right, for the IUPAC names for this, again, we need to find our ethoxy group and we need to find our parent chain. So in this, the longest carbon chain is 1, 2, 3 carbons. We have both a methyl group and an ethoxy group at carbon number 2. Ethoxy comes before methyl, so this is 2-ethoxy. And 2-methyl propane. For the next one, our longest carbon chain is 3 carbons. Now this is interesting because we actually have 3 carbons twice. So we have 1, 2, 3, and 1, 2, 3. However, we need to have our most prominent substituent at carbon number 1. So propane has the most prominent substituent at carbon number 1. So this is going to be 1-isopropoxy. So instead of isopropyl, now we have our oxygen in it. So 1-isopropoxy propane. So again, our oxygen is on carbon number 1 of our longest chain. We could have put it at carbon number 2 and said propyl, but we want it at the lowest possible number on our parent chain. So propane is our parent chain. And then we have an isopropyl group attached to our oxygen, so that makes that an isopropoxy substituent. All right, for the next ones, when you get more complicated, it's better just to do the IUPAC name for these ethers. So for this one, we have our longest parent chain, our longest carbon chain, 1, 2, 3, 4, 5 carbons. However, I want to start on this carbon. So that is carbon number 1. That's carbon number 1. That's carbon number 2. We have an ethoxy group at carbon number 2. So this is 2-ethoxy pentane. And here for our longest carbon chain, we've got carbon number 1, 2, 3, 4, 5, 6. And we have 2 substituents. Both are methoxy substituents. So both have 1 carbon attached to the oxygen. So that's a methoxy. That's a methoxy. I started here on carbon number 1, so my first substituent had the lowest possible number. So we've got methoxy at carbon number 2 and 4. So this is 2, 4 dimethoxy and we have a methyl group at carbon number 3, so 3-methyl. And again, our parent chain is 1, 2, 3, 4, 5, 6 carbons long, so 2,4-dimethoxy 3-methyl hexane.